natural disasters, climate change, overcrowding. Big problems demand even bigger solutions. It's a new era for engineering. We can build our way out of anything. In Chicago, there's no room to grow, but an underground city could house thousands. This is mega engineering.
Welcome. Please enter your floor. Minus 78. Going down. This is a Chicago Underground City Express elevator with direct connections to all residences, shops, and offices below level 50.
Chicago, Illinois, the nation's third most populous city, an iconic skyline, and an urban grid teeming with the daily rhythms of city life. But Chicago is a victim of its own success. 2.8 million people call it home, which means this great metropolis is under a daily assault. Almost 7 million commuters move in and out of the city every weekday. Even the suburbs, once an antidote to the chaos of city life, are clogged with traffic.
Despite the improvements in the interstate highway system, the traffic is still growing. In fact, there is, as in all major cities, there's an hour delay at rush hour.
When it comes to traffic, the second city is second only to New York, costing Chicagoland residents nearly 1 week per year of lost time, and the local economy over $4 billion annually. When suburbanites finally make it downtown, they find the L, one of the nation's oldest, busiest transit systems, bursting at the seams. Unable to expand to accommodate a growing ridership and an ever-widening definition of rush hour.
Well, the subway and L stations are only built for 8 cars, so therefore to increase the capacity in the system, it would be necessary to increase the size of the stations, and that would come at a very great expense.
Undeveloped land around the city is scarce, so growing out is no longer an option. And with downtown real estate at a premium, the city needs a drastic, some say groundbreaking, solution. Chicago, already home to some of the nation's tallest buildings, will have to build down. Imagine an underground city directly below the loop, over 1,300 feet deep, containing nearly 100 floors of apartments, offices, parks, and more. Room enough for tens of thousands of people to live, work, and play. It's the best solution to the Windy City space crunch.
Quite clearly you can get more people doing something or living or whatever you want to do in this underground space, where now you have very limited space on top.
It's an undertaking so big, so innovative, that it will usher in a public works project of unparalleled dimensions, challenges, and dangers. It will require excavating over 230 million cubic yards of rock, construction crews laboring tirelessly below millions of Chicagoans, to build living spaces with new methods of ventilation and lighting, to ensure that the city beneath Chicago succeeds. It won't be easy, but it may be necessary. Expanding underground is a solution that's becoming more plausible, with the emergence of new techniques to make living underground a reality.
All this is technologically doable. It comes then very quickly down to what is the other side of engineering, is what does this cost and how long does it take to build.
Chicago is an ideal place for this bold experiment. From the ashes of the Great Fire of 1871, the city grew to become the epicenter of an architectural revolution, spawning the first skyscraper in 1885 and hosting the most influential World's Fair in history in 1893. By building underground, Chicago will cement its reputation as one of the most forward-thinking cities on the planet. But it may not be the first. Amsterdam is already proposing to make space below ground where none exists above. In this Dutch city, where streetcars, pedestrians, and 550,000 bicycles compete for space along narrow streets, the volume of cars is a growing problem.
Because Amsterdam is a nice historical town and there is a lot of traffic in the town, you cannot enjoy the town because everywhere there's traffic on the channels, there's traffic on the quays, everywhere there's traffic.
Ancient city planners never foresaw a day when their picturesque byways would be overrun with automobiles. Today, there's a movement to get them off the streets. But to do that, while still maintaining Amsterdam's historic charm, it has to look towards a signature feature of its historic past: the city's canals. Amsterdam is already proposing to make space below ground where none exists above. The plan? A network of underground complexes built beneath the city's 65 miles of iconic waterways.
So we thought we bring a lot of functions who doesn't need daylight under the ground.
Parking garages, movie theaters, and shops, all built beneath miles of real estate that just happens to be filled with water.
Working in the canal space is indeed the best option, because you make from 1 square meter which has no value, you make 6 square meters which has a lot of value, of course.
In fact, the plan will convert over 20 square miles of largely untapped space and provide storage for thousands of cars. But building in Amsterdam requires sensitivity to the city's unique architecture. Amsterdam's streets can't be choked with construction equipment. Some are so narrow that the massive trucks needed to build underground won't even fit.
We don't want to have any trucks in the town because that gives an awful lot of mess, and we don't want to mess up this nice historical town.
Even if crews could access the area from sidewalks, they'd be dangerously close to the city's narrow canal houses, precariously perched above the waterways.
Let's say in Chicago, you have to drill a hole and you can place a house. It's a complete other way of building. In Amsterdam, it's not so easy to build a house because of the soil is what some call soft water.
Amsterdam's soft water, or swampy soil, makes constructing large, heavy structures nearly impossible, which is why buildings are rarely higher than 3 or 4 stories. Most of the canal houses are supported by little more than wooden piles extending into that soft water. Heavy vibration generated by construction could spell disaster. Only the canals are far enough away from buildings and wide enough to fit construction equipment. But the canals are filled with water, so engineers have proposed a solution as unique as the city itself. Amsterdam's canal system has 16 working locks, which can be closed at any time. With the locks closed, the canals can be drained.
I can imagine that people think that the most difficult thing is to bring out the water out of the canals. But in fact, that is technical one of the easiest things.
Once the canals are dry, crews will get to work, digging 30 feet down before sealing off a new surface that's both sealing to the complex below and floor to the canal above. It's a solution that will not only minimize the risk to the thousands of buildings that abut the canals, but will also keep the city from having to shut down.
Because we are working in the canal space, there is less inconvenience for the people.
Later, restoring the canals is as simple as opening the locks.
After we have finished it, the canal is exactly the same as it is now. Only there are no cars on the ground anymore, so you can enjoy the city and the nice historical houses.
The project would remove thousands of cars from sidewalks, and if it works, it could spur other cities to take up the challenge. There's just one problem. Few cities have canals from which to access their downtowns. In Chicago, there's simply no way to dig up streets without paralyzing the city and infuriating millions.
People are afraid of change. That's difficult. It's not a technical difficult, but it's very difficult to explain them. You get a better city.
Chicago may be the perfect location for this subterranean experiment, because deep beneath the glass, steel, and asphalt of this historic city lies an even richer geological past.
Well, I think it's easiest to think of Chicago geology as being a layer cake of widely differing geologic materials.
The first layer is approximately 100 feet of glacial clay, loose, soft material that's barely suitable for large structures. But beneath that lies 400 feet of limestone, strong rock that's perfect for hollowing out large chambers.
The limestone beneath Chicago is advantageous because it is stronger than concrete, typical concrete that we pour for structures.
That layer is followed by over 100 feet of shale, an unstable rock that's less ideal for building.
Shale is 5 to 10 times weaker than limestone. It is subject to this phenomenon that we call slaking. When exposed to water, it expands and fractures and degrades.
Vertical access shafts could be drilled through the shale to the next layer of limestone, which extends for another 400 feet. It's a pattern that repeats again down to 1,300 feet before hitting a deep layer of sandstone.
The top of that sandstone is weak, very weak. So weak, in fact, that it can be mined with a fire hose.
That weakness means that the underground city could go no deeper. But it's the alternating sections of limestone that make Chicago an ideal location for this feat of geological engineering. And excavating limestone is something with which Chicago is already familiar. Here at the Vulcan Mine in Naperville, Illinois, 45 minutes from downtown Chicago, an active limestone and dolomite mine has been in operation for more than 2 years, with enough material left for decades more. Today, crews will descend 400 feet to excavate the latest level of the mine. Their goal is to remove thousands of tons of rock in one day. They do it through a process called drill and blast. The drilling is taken care of by the Fletcher J352 LS. A 385 horsepower rig bores 16-foot holes into the rock, 59 holes per round, which are filled with explosives, courtesy of the ANFO loader. 2 tanks on this truck hold 5,000 pounds of ANFO, ammonia nitrate coated with fuel oil. This explosive material is injected into the holes via an air hose and set to detonate in sequence. It's a slow, methodical process.
Drilling and blasting must be conducted in a strict sequence that involves drilling, loading, evacuation, blasting, ventilation. Difficulty of transporting personnel during evacuation limits the completion to a minimum of 4 to 8 hours per round.
Safety is the utmost concern, but the process gets results. The 1,100 pounds of ANFO used in this round dislodges 1,400 tons of material and take a 14-foot layer from the wall. Drilling and blasting creates an open space where once there was a solid mass of rock. It also creates a structural engineering challenge which must be addressed immediately.
Excavating large openings causes stress concentrations that can overload the rock without reinforcement, and the larger the opening and the deeper the opening, the larger the stress concentrations.
To shore things up, another driller is on the job, boring vertical holes which are then filled with epoxy and steel bars to reinforce the ceiling. After the blast, excavated material is removed via this conveyor belt and trucked to area construction sites to be used as aggregate, a crucial ingredient in concrete that can be put to immediate use in Chicago.
If it's good material, which if you do this in the limestone in Chicago, that will be probably the case, you actually can use this material to fabricate concrete, some of which will go back into this underground city.
Well, why transport it to the surface when you can keep it down there and manufacture the city on the spot?
The underground city could use some of the material, but not all of it, leaving enough extra excavated material to pave over 30,000 miles of roads, which could stretch around the globe 1.5 times. With the ease of excavation, digging a new city is not a problem. Holding up the existing city is.
It's important to think about the depth below the foundations of the structures at which this underground city can be built.
The issue is that under these high-rise buildings, you have the large diameter piles, and under these large diameter piles, you have high loads.
Chicago's tallest building, the Sears Tower, soars to 108 stories, 1,450 feet into the air. Holding it up, 200 piles extending nearly 100 feet into the ground, sending the building's load into the surrounding rock. And that's just one building. Beneath Chicago lies a virtual forest of foundations and piles. Dig too close to them, and the buildings they support could be in trouble.
If you were to dig a hole right under the end of the pile, the lower end of the pile, quite clearly that would collapse.
For safety's sake, the first level of the underground city must be positioned hundreds of feet beneath the lowest pile. But getting there without closing city streets, rerouting miles of train lines, or redirecting sewage tunnels, water pipes, and utilities would be an enormous challenge. Avoiding them altogether would be the easiest, cheapest option.
To access the underground city, it would be important to construct that in an area where there weren't structures and utilities already.
Unable to disturb the city life above, crews will have to begin their access to the worksite from miles away.
Another possibility would be to provide this access with an incline instead of coming in vertically.
Starting from outside the city center, crews and equipment will tunnel downtown, a journey that would stop nearly 300 feet below the center of Chicago. Deep enough to avoid building foundations and city infrastructure. There, they will begin a drilling and blasting routine to construct the first level, a staging area for building even deeper. But as they do, they'll have to make sure that the walls of this new subterranean metropolis are strong enough to hold back the water of mighty Lake Michigan. Chicago is famous for two things. It's big and it's cold. But one place that's bigger and colder is Moscow. With 15 million people in the metropolitan area and over 3 million cars causing some of the worst traffic in the world, Moscow's explosive growth is putting it on a crash course with catastrophe.
The real #1 priority right now is to get rid of the transportation collapse in the city and the constant traffic jams.
To cope, the Russian capital has nowhere to go but down.
Moscow has a historic center. If we want to build anything and not ruin any historic architecture, we have to build underground.
Russia is in the middle of an underground construction boom with 2 new projects that aim to save the city from its own success. The first, Tverskaya Mall, will be the biggest underground mall in all of Europe when it's finished. 4 stories deep, spanning over 350,000 square feet. Russia is in the middle of an underground construction boom. The first, Tverskaya Mall, will be the biggest underground mall in all of Europe when it's finished. But building it means redirecting nearly 294,000 cars that creep through adjacent streets each day. And crews must work perilously close to traffic. The second site, Paveletsky Square, will one day be a 5-story deep shopping and parking complex, integrated with the train station that sits above it. But before that plan is realized, crews must cope with the city's soft, muddy soil. The soft soil doesn't pose a problem when erecting the shorter buildings that are the city's signature. But it's not ideally suited for building underground. Just to get to a firm enough stratum for building means digging down over 90 feet to stiffer, stronger clay. Back at Paveletsky Square, the crew knows those challenges all too well. Digging one giant hole for an underground mall isn't an option. Not when Moscow's loose, muddy soil is so hard to hold back. So today, instead of digging space for the complex and then lining it with concrete walls, they're doing the opposite, building the walls first. That's the job of this excavator. 6 sets of blades dig through the slop, cutting a 2-foot wide chamber that is almost immediately filled with concrete, forming walls to a complex that is yet to be hollowed out. It's slow and laborious, requiring frequent starts and stops just to clean it. But once the walls are set, crews can continue digging. But the challenge doesn't end after the walls are in place. Digging in a city means rerouting utilities, sewage lines, and other infrastructure. Eventually, crews will be able to hollow out this section of Paveletsky Mall. Like on the other side of the worksite, where crews are now 100 feet deep, lining the walls with steel rebar, concrete, and plastic. With so much water dripping through, the risk of cave-ins is still all too real. That's why these giant poles, 5 feet in diameter, some 200 feet in length, are put in to hold back the walls. Despite their massive size, they're temporary, removed once the entire box is reinforced. Because water always finds the weakest path, engineers must be vigilant, even though Paveletsky Square is half a mile from the Moscow River. Imagine the dangers crews would face halfway around the world, back in Chicago. A city perched on the shores of a great lake.
One could imagine Lake Michigan being right there. How does one control all that water from getting into an underground structure?
Allowing water to seep in could lead to disaster. Each level of Chicago's underground city would have to be painstakingly reinforced in order to stay ahead of a population boom that threatens to strangle the city. The underground city would have to be built quickly. One day, Chicago's underground city will look less like this and more like this. Ochotny Riyadh, Moscow's biggest underground mall. With 3 stories of shopping and dining, it's a place where thousands of Muscovites can escape the cold. It's just like Chicago's underground city of the future. The mall is hidden in plain sight, mere steps from the center of the city. For Chicago's underground city to even begin to approach the comfort of Moscow's underground mall, it will have to address a huge issue. In any mine, air quality is a priority. During construction, engineers can employ a ventilation method in use at the nearby Vulcan mine. This vertical shaft works to pull air in from the mine's access tunnels and directly up, making sure that dust and other contaminants don't linger for too long. This is a system meant to provide comfort and security to dozens of miners working 10-hour shifts. Replace them with thousands of residents living underground 24 hours a day, and the ventilation needs become far more complex.
People will have to occupy these spaces for 50 to 100 years, whereas miners occupy the spaces for single digits of years as opposed to multiple decades.
Deep beneath the ground, there will be no open windows, no breezes to keep fresh air circulating. Ventilation is a problem that's already been solved, far beyond the needs of any underground city in Boston, Massachusetts. Here, engineers behind the Big Dig, the most expensive public works project in U.S. history, were faced with thousands of cars passing through almost 4 miles of tunnels every day, spewing tons of poisonous exhaust. Moving vehicles push air through the tunnels, but traffic jams can cause air to linger and dangerous gases to build up. So the Massachusetts Turnpike Authority installed a complex ventilation system to keep the air moving. Near tunnel openings, jet fans circulate air. But with some tunnels as deep as 120 feet, Boston had to go to more extreme measures to bring air underground. Deep beneath this building in the heart of Boston lie the lungs of the Central Artery Tunnel System. A building 125 feet tall pulls in fresh air and transfers it to the tunnels below.
The intake air is sucked in through those louvers, as you see behind me, and it's sucked down to a fan chamber and through a series of tunnels or conduit into the tunnel.
100 feet below ground, in a massive intake room, giant fans pull fresh air down the shaft. 400 horsepower engines are capable of moving 333,000 cubic feet per minute and generating wind speeds of up to 62 miles per hour. It's a powerful system based on age-old techniques.
All the components of the Big Dig basically used tried and true technology. The hardware and the mechanical equipment performing the ventilation is pretty much a century old now.
It takes 13 buildings like this to cover Boston's tunnels. And while the means of moving air hasn't changed in years, the ability to adjust to the changing needs of an underground environment has.
Basically, we have a surveillance in the tunnels. We have cameras watching the traffic. Almost all of our cameras and sensors are monitored from our operations control center.
Inside the Massachusetts Turnpike Authority building, at the Operations Control Center, specialists monitor 32 vent zones and control 235 fans and over 500 cameras with just the push of a button. They're concerned with air quality and a lot more.
More than just the ventilation is monitored there, the pumping of water, the traffic conditions in general, so you really get a very efficient management of all the life safety functions within all the tunnels under one roof.
But this centralized command center has some fail-safe backups. Even if communication with one of the vent buildings is lost, each vent tower is staffed and powered independently.
There are local controls within the vent buildings that we can still operate the fans by in a manual mode with personnel.
Chicago's underground city will apply much of the technology used in Boston, only at 10 times the depth. The underground city's walls and floors will be lined with ventilation chambers. Fans at the bottom of the city will pull fresh air in through intake shafts located at the top, where it will descend down 1,300 feet and circulate throughout the city before returning to the surface to be exhausted. Regulating the airflow would require the kind of sharp monitoring used in Boston.
You're living down there, so it's not just a transient air, and I'm sure you would probably have a much stricter requirement for the cleanliness of the air that you're breathing.
Regulating air quality for a 24-hour residential population, and not just automobile traffic, would require many more fans and a control system that would be the eyes and ears of an underground city. It's something that would provide security and peace of mind for the residents beneath Chicago should the unthinkable happen. With the underground city a reality, one factor of Chicago's legendary climate will be mitigated, if not eliminated altogether.
Well, there are advantages to living underground. For instance, you're not subjected to the vagaries of Chicago winters.
Deep beneath the city streets, residents wouldn't have to worry about snow or even staying warm. Because if there's one thing about living underground that's predictable, it's the temperature.
Well, no matter how hot or cold it is in the air in Chicago, 20 feet underground, it's around 55 degrees Fahrenheit, no matter the time of the year.
But the deeper you get, the warmer it becomes, thanks to something called the geothermal gradient. On the surface, temperatures are affected by the sun and atmospheric changes, but up to 200 feet below ground, the temperature remains constant. Then, for every 100 feet deeper, the temperature rises about 1 degree Fahrenheit. Fortunately, in the underground city, the geological limits of construction would ensure that things didn't get too toasty.
I think it might be nice to be constantly at 65 to 68 degrees Fahrenheit than it would be the highly variable 0 to 100 degrees Fahrenheit at the surface.
An unvarying climate is one advantage that the underground city will have over its surface level counterpart. But there's one quality to which the underground city can't hold a candle.
Possibly the most important issue would be the lighting itself, because without artificial illumination down there, it's completely black.
Daylight, so vital to health and human happiness, can only come from one source. Even in Moscow, with just 70 sunny days per year, the underground mall Ochotny Riyadh does what it can. With skylights that decorate the roof of the mall, allowing sunlight to travel 3 stories underground. It's a solution that'll work in Chicago too, up to a point. Massive skylights will illuminate the structure's uppermost levels, but deeper down there would be no way for sunlight to reach people. This simple fact would make opting for a life above ground, in spite of Chicago's cold, worth it to many. But if a solution exists, it may be found at Rensselaer's Polytechnic Institute's Lighting Research Center in Troy, New York. Here, researchers focus on light's effects on health and the circadian system, the 24-hour cycle that all humans are programmed to follow.
The circadian system wants to see a regular 24-hour pattern. And that is the pattern that we evolutionarily grew up with. It's in the last 100 years that we have electric light that allows us to extend light into the nighttime. But what's also happened in the last 100 years, we live indoors.
With that move indoors to offices and homes with electric lighting, humans have disrupted the light-dark pattern that regulates the circadian system.
We can be in perfectly good light to see, and yet we can be in biological darkness. You can't necessarily stimulate the circadian system with electric lighting.
With only artificial light, the internal clocks of underground citizens would go haywire.
The circadian system is a clock that runs all the time anyway. And if you don't have a resetting of that clock, a synchronization of the sunrise, sunset, you can go into this architectural jet lag, as we call it.
To maintain this synchronization, engineers will have to design lighting systems that mimic the patterns on the surface. But even these artificial means don't go far enough. Massive skylights will illuminate the structure's uppermost levels, but deeper down there would be no way for sunlight to reach people. This simple fact would make opting for a life above ground, in spite of Chicago's cold, worth it to many. Engineers will have to design lighting systems that mimic the patterns on the surface. But even these artificial means don't go far enough.
It is important not just how much light you get, but when you're getting the light and what kind of light you're getting.
In the Light Research Center's lab, a test measures light's effects on brain activity. Hooked up to an EEG, a subject is exposed to different wavelengths of light. While all wavelengths stimulate the brain, blue light is the most effective.
The reason why we're working with blue light is because we have shown that the circadian system is maximally sensitive to blue light.
That may be because the color of the sky has programmed our brains to respond to the blue wavelength of visible light. RPI has found that the need for blue light is so ingrained into human DNA that it only takes a small amount to trigger alertness.
So this way you can effectively achieve the same result in reducing melatonin levels or increasing brain activities with less amount of power or with less light. So it's an energy efficient way of impacting the circadian system.
That energy savings would preclude the city from having to bathe common areas in blue light or from running ultra-hot lights to simulate sunlight. Instead, residents could take a more personal approach.
Blue light is so effective for the circadian system. We can get very low levels of blue light and be able to impact the circadian system.
Brief exposure to blue light is as effective as using a more common method for waking up.
What you can do is, just like a cup of coffee, you can use light for 15 minutes, 20 minutes to perk you up and to give you some alerting stimulus.
There would be lots of opportunities to manipulate that light in such a way that it can provide a sense of daytime and nighttime, can provide a sense of change, and can provide a sense of difference that makes life enjoyable. It's the differences in life that I think we find attractive.
It's not only life below Chicago that would begin to improve. At street level, the city will find smaller crowds, less traffic, and a transportation system more able to cope when people are no longer commuting from outside of the city, but from underneath it.
Well, the city could be beautified if much of it were placed underground. Placing the major functions underground will allow us to think more expansively of the most appropriate uses of the surface land.
That's just what happened in Boston after the Big Dig.
The city has been knitted together again, if you will. Some of the surface land has been reclaimed for public use versus having an elevated highway on it. There are now parks where there were steel structures before.
Those above-ground improvements could go a long way towards generating support to expand the underground city. But continuing to hollow out the ground beneath Chicago's skyscrapers could be met with opposition. So the underground city will have to navigate uncharted territory.
Well, the state of Illinois owns the lake bottom from the shore outward, and there are no buildings there. Perhaps it might be a great deal less expensive and more quickly realized to actually excavate the underground city indexed over by the lakeshore.
By connecting a new network of underground chambers to the existing underground city, urban planners could create a mirror image of the city beneath the lake.
In terms of changing the way in which the world thinks of Chicago, it might move it out of the realm of its current beautiful vertical skyline to thinking about maybe its underground skyline.
There's just one problem. The first part of the underground city was built without anyone living there. The challenges that once only affected crews could now have an impact on thousands of permanent underground residents.
You'll never be able to see the complete picture underground as you will above ground. So the unknowns are basically higher, and you have to deal with that during construction.
Most important issue to address would be the possibility of any types of historic gas deposits that are located there.
If crews accidentally stumbled upon a hidden gas line, the consequences could be disastrous. Evacuation plans would share much in common with those in place for skyscrapers.
One can only think about the situation for tall buildings now. How many elevators would be necessary? How many stairwell cores would be necessary? Those same discussions would have to be held for the underground facility as well.
But thousands of feet below ground, those considerations would be flipped upside down. With elevators inoperable, stairs would be the only means of egress. Those at the bottom levels would have to climb the equivalent of a 100-story building to escape. Not an option for the very young, elderly, or handicapped. Emergencies would require fast thinking and fast acting on the part of city officials, who would seal off trouble spots, protecting the rest of the city by flushing out dangerous gases. The technological challenges of building underground can be overcome.
It will cost more or will cost less. But from a technical point of view, there's not much left today that we cannot do.
The psychological challenges are another story.
The question is, how much time would people spend on the ground? Where's the limit where people would say, no, I don't want to do that?
But with cities bursting at the seams, struggling to keep up with a population boom, those concerns may be overridden by practical necessity. It will take some time for Chicagoans to accept the necessity of living underground.
10, 15 generations from now, if people have been exposed to nothing else but living underground, they will accept that.
I think that, to be quite honest, humans are very robust species, and they do get used to things that you don't believe they get used to. So I think humans would get used to living underground, and I would get used to living underground too.
One day, people around the world will do more than just shop or drive underground. One day, we just may live there.